That glowing cloud in Orion's sword hides a universe of chaos. The Orion Nebula is not just a beautiful cosmic portrait, it is a stellar nursery and a hotbed of bizarre phenomena. By the end of this journey, you will understand why this iconic cloud is one of the most important and violent laboratories in our galaxy. We will uncover infant solar systems being born and torn apart, cosmic bullets fired by an unseen cannon, and the secret ingredients for life brewing in the darkness. What is the most surprising secret a place of beauty can keep? One of its most recognizable features is also a profound cosmic mystery. Cutting across the nebula's glowing heart is a dark, sharp-edged lane astronomers call the Orion Bar. At first glance, it looks like a solid wall of dust, a simple divider in the celestial cloud. The truth is far more dynamic. This bar is not an object at all, but a violent frontier. It is a photodissociation region, a place where the furious energy from the nebula's newborn stars meets the cold, dense material of the surrounding molecular cloud. The primary architects of this chaos are the brilliant, massive stars of the Trapezium cluster. Their intense ultraviolet radiation acts like a relentless cosmic sandblaster, slamming into the cloud's edge. This radiation is so powerful it literally tears molecules apart, stripping electrons from atoms in a process we call photodissociation. What we see as that dark bar is actually the shadowed side of a towering, glowing wall of gas, one of the largest and closest natural laboratories of its kind in our galaxy. Here, in this turbulent zone, the very building blocks of cosmic chemistry are shattered and then reassembled under extreme conditions. Simple hydrogen molecules are ripped into individual atoms, while more complex carbon-bearing molecules are broken down, only to recombine into new, often more resilient forms on the cooler, shielded side of the frontier. This ongoing cycle of destruction and creation makes the Orion Bar a crucial site for understanding how complex chemical compounds, some of which are precursors to the ingredients for life, can form even in the most hostile environments. It is a vivid demonstration that in space, even apparent emptiness is a scene of furious activity, a constant battle between light and shadow that forges the universe's future chemistry. This furious battle between starlight and shadow sets the stage for creation on an even grander scale. Nestled within the nebula's turbulent clouds, astronomers have found the very cradles of new worlds. They are called proplids, a shorthand for protoplanetary disks, and they are infant solar systems caught in the act of being born. The Hubble Space Telescope gave us our first clear family portrait of these cosmic nurseries, revealing them not as mere specks but as distinct, intricate structures. Some appear as dark silhouettes backlit by the nebula's glow, like black holes punched in a luminous canvas. Others shine as tiny, glowing halos around their central baby stars, their dust and gas illuminated from within. Each one is a swirling, flattened disk of leftover material from the star's own formation, a vast construction zone hundreds of times wider than our entire solar system. Within these spinning disks of gas and dust, the future is being written. Through countless gentle collisions over millions of years, microscopic particles will stick together, growing into pebbles, then rocks, then planetesimals, and finally full-fledged planets. The sheer abundance of proplids in the Orion Nebula is perhaps the most profound revelation. Hubble found them everywhere, surrounding scores of young stars. This tells us that planet formation is not a rare or special event in the cosmos, but a common, almost inevitable chapter in the life story of a star. Our own solar system once looked just like these faint, glowing disks. Every star you see in the night sky likely hosted a similar disk in its youth, and many of those disks have now transformed into families of planets, some of which may harbor conditions for life. To gaze upon a proplid is to look back in time, to witness the very beginnings of our own cosmic home. But the story in Orion is not always one of peaceful construction, for these delicate cradles exist in a very dangerous neighborhood. These delicate disks of future worlds exist in a crucible of unimaginable force. At the very heart of the Orion Nebula lies the engine of all this chaos, a tight-knit family of 4 brilliant, massive stars known as the Trapezium cluster. They are not gentle suns, these are stellar titans, each many times more massive and hundreds of thousands of times brighter than our own sun. Their influence is not passive, it is an active, violent sculpting. Beyond their searing ultraviolet light, these stars unleash torrents of charged particles moving at supersonic speeds, a phenomenon astronomers call stellar winds. Think of it not as a breeze, but as a continuous hypersonic hurricane blowing from the surface of each star. These winds collide with the surrounding cloud of gas and dust with the force of a perpetual explosion. They act like cosmic blowtorches, carving out vast cavities and bubbles within the nebula's structure, pushing the interstellar material outward and clearing the space around the cluster itself. This creates the very hollows and glowing walls we see in images of the nebula. The architecture of the nursery is literally being shaped by the breath of its most powerful children. This process has a profound dual nature, a cycle of creation and destruction. As the stellar winds slam into the surrounding molecular cloud, they compress the material at their edges. Just like squeezing a lump of clay, this compression can trigger gravitational collapse in dense pockets, forcing them to contract and heat up until new stars ignite. In this way, the Trapezium stars are midwives to the next generation, their violence sparking birth. Yet, in the very same act, they are sealing the nebula's fate. By relentlessly blowing away the gas and dust, they are dispersing the raw material of future stars and planets. They are essentially evaporating their own birthplace. This means the Orion Nebula, as a stellar nursery, has a limited lifespan. In perhaps a few 100,000 more years, a mere blink in cosmic time, these fierce winds will have scoured the region clean. The glorious glowing cloud will fade, leaving behind an open cluster of stars against the dark backdrop of space, its nursery days forever over. The beauty we see today is therefore transient, a spectacular but fleeting phase in an endless cycle. But for every brilliant Trapezium star blazing in plain sight, there are secrets still cloaked in darkness. Deep within the thickest clouds of the Orion Nebula, far from the reach of visible light, lies one of its most profound enigmas. It is known as the Nebula object, a name that sounds more like a classified project than a star, and in a way it is. This object is not seen, it is sensed. At the wavelengths our eyes perceive, it is utterly invisible, completely smothered by the dense, dusty cocoon that surrounds it. We only know it exists because of its intense infrared glow, the heat signature of an immense cosmic engine buried alive. This hidden titan is a protostar, a star in the very earliest stages of its formation. It is so young that it has not yet begun to fuse hydrogen in its core, the process that defines a true star. Instead, it shines from the colossal energy of its own violent birth, the gravitational collapse of an entire cloud of gas converting into searing heat. The Nebula object is not just any infant star, however. It is a massive protostar destined to become a stellar heavyweight many times larger than our Sun. Its obscurity is its greatest scientific gift. It offers us a rare, direct glimpse into the most secretive and briefest chapter in the life of a giant star. The brilliant, visible stars of the Trapezium have already cleared their surroundings, blowing away their dusty birth blankets. But the Nebula object is caught in the act, still swaddled in the dense material from which it is forming. Studying it is like having a window into a hidden nursery room, allowing astronomers to understand the conditions and processes that govern the birth of the most influential stars in the galaxy. These massive stars live fast and die young, shaping their surroundings with ferocious winds and radiation, and ultimately exploding as supernova to seed the galaxy with heavy elements. The Orion Nebula object represents the very beginning of that dramatic life cycle, a hidden giant taking its first breaths in the dark, reminding us that the most important events in the cosmos often happen out of view. This hidden giant is not alone in the dark. Just a short cosmic distance from the Orion Nebula object lies another, even more intense knot of hidden activity, a place known as the Kleinman Nebula. If the Orion Nebula is a sprawling stellar city, then this region is its dense, fiery industrial district. Unlike the glowing visible nebula, the Kleinman Nebula reveals itself almost exclusively in the infrared, a seething core of gas and dust so thick it blocks all visible light from escaping. This is not a quiet cloud, it is a frenzied powerhouse of star formation operating at an incredible scale. Within this compact, shrouded volume, astronomers have discovered an entire cluster of incredibly young and massive stars, all crammed together and still embedded in their dusty birth cocoons. The energy output here is staggering, making it the true engine room driving much of the turbulence we see in the wider Orion complex. The processes at work are raw and violent. Gravity is in a relentless tug of war with the very stars it creates. As dense pockets within the nebula collapse under their own weight to form new stars, those stars immediately begin fighting back. Once ignited, their fierce radiation and powerful stellar winds blast outward, trying to push away the surrounding material that feeds them. This creates colossal, high-speed jets and molecular outflows, streams of gas shot out from the poles of the infant stars like cosmic fire hoses. These outflows slam into the surrounding cloud, carving chaotic cavities and triggering shockwaves that can, in turn, compress other parts of the cloud and spark even more star formation. It is a self-regulating, incredibly messy cycle of birth and feedback. The Kleinman Nebula is a perfect illustration of how star formation is not a gentle, orderly process, but a chaotic, almost explosive one. This hidden engine, churning away in infrared darkness, is ultimately responsible for shaping the beautiful visible nebula we admire. Its fierce activity seeds the region with new stars and stirs the cosmic pot, ensuring that the Orion Nebula remains one of the most dynamic and fascinating laboratories in our galactic neighborhood. This violent feedback from newborn stars announces itself in spectacular fashion. If you look closely at high-resolution images of the Orion Nebula, you can sometimes spot small, glowing knots or bow-shaped structures, seemingly disconnected from the main cloud. These are not stars, but something far more fleeting and energetic. They are called Herbig-Haro objects, and they are the brilliant birth cries of infant suns. Each one is a luminous shockwave, a cosmic sonic boom made visible. They form when powerful, narrow jets of gas erupt from the poles of a deeply embedded protostar. As this star gathers material from its surrounding disk, a portion of that material gets funneled along magnetic field lines and blasted back out into space at speeds of hundreds of kilometers per second. These supersonic jets then slam into the slower-moving gas of the surrounding nebula, creating a violent collision. The impact heats the gas to incredible temperatures, causing it to glow brightly and creating the distinct, often symmetrical shapes we observe. In Orion, famous pairs like HH1 and HH2 serve as perfect textbook examples. They appear as two bright, compact clouds racing away from each other in opposite directions, launched from an unseen star between them. Watching them over time, astronomers have measured their motion, confirming they are indeed blasting outward, changing shape from year to year. These objects are more than just pretty lights, they are vital tracers. Because they are so bright and their jets punch through the surrounding dust, Herbig-Haro objects act like glowing signposts, pointing directly to the location of a very young, active star that might otherwise be completely hidden. They reveal the dynamic, often messy process of stellar accretion, showing us that even as a star builds itself by pulling material in, it is also violently expelling some of it back out. This expulsion is a crucial part of the star's development, a way for it to shed excess angular momentum and stabilize. To witness a Herbig-Haro object is to see the raw, unfiltered physics of star birth, a brilliant and temporary signature of a cosmic toddler learning to control its own power. This dramatic game of stellar pinball has left tangible evidence racing through space. Among the most compelling mysteries in Orion are the massive runaway stars, celestial bodies moving so fast they are essentially escaping the nebula. Two of the most famous are known simply as the Nebula object, which we've already met as a hidden protostar, and another enigmatic source called Source I. What makes them extraordinary is their motion. Precise radio telescope measurements have tracked them flying apart from a common point of origin near the Trapezium cluster at astonishing speeds. They are not just drifting, they are being flung like stones from a slingshot, moving fast enough to eventually leave the Orion Nebula entirely. The leading explanation for this stellar ejection is a process called dynamical interaction, a gravitational game of cosmic pinball that plays out in the crowded nurseries where stars are born. In the dense core of a young cluster like the one in Orion, stars are not spaced neatly apart. They are packed together, orbiting in a chaotic gravitational dance. When two or more massive stars pass extremely close to one another, their immense gravity can interact in a violent slingshot maneuver. One star can absorb the kinetic energy of the others, getting a tremendous gravitational kick that sends it hurtling out of the cluster at high speed. In some scenarios, a close three-body encounter can even result in one star being ejected while the other two become a tighter binary pair, a sort of stellar divorce with extreme consequences. This is likely what happened to the Nebula object and Source I. A close gravitational encounter, perhaps involving the massive Trapezium stars themselves, acted as a natural particle accelerator, launching these enormous infant stars on trajectories that will take them across the galaxy. These runaways are not just curiosities, they are critical to understanding how star clusters evolve. By ejecting their most massive members, these dynamical interactions prevent the cluster core from becoming too dense and unstable. It is a self-regulating safety valve. Furthermore, these runaway stars carry the story of their birthplace with them. As they travel, they will eventually die, often in spectacular supernova explosions far from their original home, seeding distant regions of space with the heavy elements forged in their cores. So the next time you look at Orion, remember that some of its most powerful children are already on an epic journey into the void, cast out by the very chaos that created them. The same forces that can fling entire stars can also fire far stranger ammunition. In 2005, astronomers using the Gemini Observatory in Hawaii discovered one of the Orion Nebula's most violent and peculiar phenomena. They are known as the Orion bullets, and the name is perfectly literal. These are not stars or planets, but compact, bullet-shaped knots of glowing gas, each roughly 10 times the size of our entire solar system. They are streaking outward from the nebula's core at impossible speeds, over 400 kilometers per second. At that velocity, you could travel from Earth to the Moon in under 20 minutes. What makes them visible is their unique composition. They are rich in iron gas, which glows with a specific blue hue in the observatory's images, leaving brilliant conical wakes of shocked hydrogen gas behind them like cosmic contrails. Their existence points to a cataclysm of unimaginable power hidden within the dusty heart of the Kleinman Low region. The leading theory suggests these bullets are the shrapnel from a colossal explosion that occurred roughly 1,000 years ago. One compelling possibility is that they were blasted outward by a supernova, the final, detonative death of a massive star. Yet, curiously, we see no obvious supernova remnant there today. Another, even more dramatic idea is that they were forged in a stellar collision, a direct, catastrophic merger of two young stars or protostars in that overcrowded nursery. Such an impact would release a titanic burst of energy, ejecting massive blobs of stellar material at hypersonic speeds. These bullets are therefore more than just speeding clouds, they are forensic evidence. Each one is a tracer round, marking the path of a shockwave from a single, violent event that continues to reverberate through the nebula. They show us that the nursery is not just a place of gradual birth, but also of sudden, apocalyptic violence, where the very processes of creation can sometimes resemble destruction. While the bullets are evidence of sudden violence, other structures in the nebula reveal a slower, more patient sculptor at work. Winding its way through the glowing gas is a prominent, snake-like feature astronomers call the integral-shaped filament. From a distance, it looks like a graceful, curving river of dust and faint light, a beautiful but seemingly passive part of the scenery. Its true nature, however, is anything but passive. This filament is a colossal thread of dense gas and dust, a backbone within the chaotic cloud. What gives it that distinctive, coherent shape is not random chance, but an invisible cosmic force, magnetism. The entire Orion Nebula is threaded with magnetic fields, lines of force that run through space like an immense, unseen spiderweb. The integral-shaped filament has formed along one of these powerful magnetic lines. Think of it like iron filings aligning themselves along the field lines of a bar magnet. The charged particles and dust grains within the nebula are influenced by this magnetism, causing them to slowly drift and gather along these invisible tracks over immense stretches of time. This process organizes the chaos, channeling the raw material of the cloud into long, dense ropes. This is where the filament's role becomes crucial for star birth. Gravity wants to pull a cloud of gas inward to form a star, but it needs a starting point, dense enough not to begin the collapse. The magnetic fields, by shaping and compressing gas into these long filaments, create the perfect conditions. Denser clumps can form along the filament like beads on a string. Once a clump reaches a critical density, gravity can overcome the supporting pressure of the magnetic field and take over, causing that specific bead to contract into a protostar. So the integral-shaped filament is more than a pretty curve. It is a cosmic conveyor belt, a magnetic highway that guides and feeds the process of stellar birth. By studying its structure and the motion of gas within it, astronomers can trace the invisible magnetic skeleton of the nursery, understanding how this fundamental force orchestrates the construction of stars from the very first step, proving that even in the apparent randomness of a nebula, there is an underlying order written in lines of force. Magnetism organizes the chaos, but the nebula also broadcasts its own strange signals. Among the most unusual is a phenomenon that turns simple molecules into natural cosmic lasers. They are called methanol masers, and they shine not with light but with intense, focused beams of microwave radiation. The word maser stands for microwave amplification by stimulated emission of radiation. It is essentially a laser, but operating at much longer microwave wavelengths instead of visible light. In the dense, turbulent cores of star-forming regions like the Kleinman Low Nebula, conditions are just right for these natural amplifiers to switch on. Here, shockwaves from protostellar jets or violent outflows slam into clouds rich in methanol, a simple organic molecule often called wood alcohol. These shocks pump energy into the methanol molecules, exciting them. When another microwave photon passes by, it can stimulate these excited molecules to release their stored energy, emitting an identical photon in perfect sync. This process creates a chain reaction, amplifying a weak signal into a powerful, coherent beam. The result is an exceptionally bright and pinpoint source of microwave emission, a brilliant beacon in the radio sky that stands out starkly against the background. For astronomers, these masers are invaluable signposts. They act as nature's own highlighter pens, marking the exact locations of the most energetic and hidden activity. A bright methanol maser often flags the precise spot where a massive protostar is forming, still buried in its dusty cocoon, or where a high-speed jet from a newborn star is violently interacting with the surrounding cloud. By mapping these mazes, scientists can trace structures and motions within the obscured hearts of stellar nurseries with incredible precision, listening in on the intense whispers of creation that ordinary telescopes could never see. The nebula's own light show is not a fixed display. For centuries, sharp-eyed astronomers have documented something peculiar about the great Orion Nebula. It changes. From one decade to the next, its glow seems to shift, with certain regions mysteriously brightening or dimming. The most famous case occurred in the late 19th century, when astronomers like Sir John Herschel and others noted a dramatic fading in the nebula's northwestern region, an area that had been prominently bright just decades before. This was not an error in observation, it was a real transformation happening in real time on a cosmic scale. The explanation lies in the dynamic, three-dimensional nature of this stellar nursery. The nebula is not a flat painting on the sky. It is a deep, churning volume of gas and dust illuminated from within by the brilliant but variable Trapezium stars. What we perceive as a change in brightness is often a trick of celestial shadow play. Dense, dark clouds of dust drift through the foreground, casting moving shadows across the glowing background gas. A single, small cloud passing between us and a bright patch of nebula can make that region appear to fade over years, just as a cloud dims the sun. Conversely, if a shadowing cloud moves out of the way, a previously dim area can suddenly seem to ignite. The illuminating stars themselves can also contribute. Massive young stars are often unstable, prone to sudden flares or variations in their fierce ultraviolet output. A slight dip in the intensity of the Trapezium stars could cause the entire nebula's fluorescent glow to dim slightly, like a cosmic dimmer switch being turned down. Finally, the gas itself is in constant turbulent motion, expanding and shifting in density. A region might brighten simply because a shock wave has compressed it, making it glow more intensely. So the variability of the Orion Nebula is not a sign of something dying, but a proof of its vibrant, living nature. It is a colossal, ever-changing sculpture of light and shadow, reminding us that the cosmos is never truly still. This constant state of change is driven by something far more fundamental than shifting shadows. The Orion Nebula is not a serene cloud, it is a violently churning sea of gas. The motions within it are not gentle drifts but chaotic, supersonic storms. If you could stand within the nebula, the silence would be an illusion, for the gas around you would be ripping past at speeds exceeding 400,000 miles per hour, faster than the speed of sound. This is not a single wind but a cacophony of collisions. The furious stellar winds from the Trapezium stars blast outward, crashing into the slower moving walls of the molecular cloud. The high-speed jets from Herbig-Haro objects punch through the dense material like underwater torpedoes, and the shock waves from past cataclysms, like the event that fired the Orion bullets, continue to expand and reverberate through the volume. All of these forces combine to create a state of extreme turbulence, a cosmic whirlpool where eddies and whirlwinds span distances larger than our solar system. This turbulence is not just a side effect, it is a crucial architect of the nursery itself. It plays a paradoxical role, both a barrier and a catalyst for star birth. On one hand, the chaotic, buffeting motions create a kind of internal pressure that supports the cloud against its own gravity. This can prevent a region from collapsing too quickly, essentially stirring the pot so vigorously that the material cannot easily clump together. On the other hand, when these turbulent flows collide head-on, they can create incredibly dense, compressed knots. It is like two ocean waves crashing together and throwing spray high into the air. Only here, the spray is a pocket of gas squeezed so tightly that gravity finally wins, seizing the opportunity to initiate collapse and spark a new star. This delicate balance means the nebula is in a constant, dynamic equilibrium, with turbulence regulating the pace of construction. Without this supersonic chaos, the entire cloud might have collapsed into stars in a single, brief burst long ago. Instead, the turmoil stretches the process out over millions of years, allowing for multiple generations of stars to form and ensuring the nursery remains a bustling, evolving ecosystem. This supersonic turmoil does more than just sculpt stars, it also stirs a cosmic chemistry set of astonishing complexity. Within the cold, dark depths of the Orion Nebula, far from the destructive ultraviolet glare of the Trapezium, radio telescopes have detected a rich broth of molecules that reads like the inventory of an alien laboratory. We find simple methanol and formaldehyde, but also more elaborate compounds like methyl cyanide and even glycolaldehyde, a simple sugar molecule that is a direct precursor to amino acids, the building blocks of proteins. Orion, it turns out, is not just a stellar nursery. It is a cosmic brewery, quietly assembling the fundamental organic ingredients for life amidst the chaos of creation. These molecules cannot form in the hot, diffuse gas of the bright nebula where radiation would tear them apart. Instead, they are crafted in the frigid, shielded cocoons of the dense molecular cloud on the surfaces of something seemingly insignificant interstellar dust grains. These microscopic particles of silicate and carbon act as tiny, frozen factories. In the deep cold of space, just a few degrees above absolute zero, atoms and simple molecules like carbon monoxide and water freeze onto these dust grains, forming icy mantles. On this frozen stage, cosmic rays and occasional pockets of heat provide just enough energy for the trapped atoms to shuffle and bond, building up more complex organic molecules over millions of years. When a young star finally ignites nearby, its warmth can sublimate these icy mantles, releasing their complex molecular harvest into the surrounding gas, where our radio telescopes can finally detect their faint, telltale signatures. The profound implication is that the basic chemical precursors for life are not rare or special. They appear to be a standard byproduct of the star-forming process itself, woven into the fabric of stellar nurseries across the galaxy. Every swirling disk around a newborn star in Orion is likely being seeded with this organic soup, suggesting that the raw materials for biology are being delivered to infant planetary systems from their very first moments. That rich organic soup brewing in the dark does not stay hidden forever. It is often revealed by a dramatic play of light and shadow, and one of the most famous examples sits right at the edge of the nebula's brightest region. Look closely at the area just southwest of the brilliant Trapezium stars, and you will see a prominent, dark intrusion, a deep bay of blackness that seems to bite into the glowing gas. Astronomers have long called this feature the fish's mouth. It is not a hole or a void, but a mountain, a towering, thick cloud of cold gas and dust so dense that it completely blocks the intense light from the nebula behind it. What we see is a colossal silhouette, a cosmic shadow cast against a brilliant backdrop. This dark bay is a classic example of a dark nebula, a cold, dense knot within the larger molecular cloud that birthed the Orion stars. While the Trapezium's radiation has evaporated and blown away much of the surrounding material, this cloud is stubborn. Its sheer density provides a shield, allowing it to withstand, for now, the relentless stellar winds. Within its frigid depths, temperatures plummet to just a few tens of degrees above absolute zero. Here, the chaotic turbulence of the nebula is muted, replaced by a deep, cold quiet. And it is in this profound quiet that the future may be quietly assembling itself. The fish's mouth and structures like it are not just scenic features. They are cold storage. They are dense reservoirs of the very same gas and dust that formed the Trapezium stars, material that was passed over in the first wave of star formation. Shielded from the destructive radiation, the delicate molecules and ices within this dark cloud can continue to grow and complexify. Most intriguingly, the immense gravitational pull of all that concentrated mass may already be at work. Subtle tugs and instabilities within the cloud could be causing it to fragment internally, collapsing into dense cores that will one day ignite as the next generation of stars. So this dramatic shadow is far from a dead end. It is a waiting room, a protected vault where the raw ingredients of future solar systems are being kept safe, hidden in plain sight until the chaos of the current era subsides enough for a new cycle of birth to begin. The shadowy vault of the fish's mouth offers a temporary refuge, but for many infant solar systems in Orion, there is no such shelter. For the proplyds that drift too close to the brilliant heart of the nebula, their very existence becomes a desperate race against an evaporating sun. The same ultraviolet radiation that makes the nebula glow is, for these protoplanetary disks, a deadly inferno. The Trapezium stars act like cosmic blowtorches, their intense energy boiling away the outer layers of gas from the proplyds in a process astronomers call photoevaporation. We can actually see this happening. Hubble images show many of these disks with spectacular, comet-like tails streaming away from them, pointing directly opposite the direction of the Trapezium cluster. These are not tails of dust and ice, but of gas being violently stripped away, ionized by the starlight, and blown into space by the relentless pressure of the radiation. It is a stunning and sobering sight, watching the raw material for future planets being systematically erased. This creates a profound cosmic dilemma. We know planets form through the slow, gentle accumulation of dust and gas within these disks over millions of years. But photoevaporation works on a much shorter timescale, potentially dispersing an entire disk in just a few 100,000 years. So the question becomes a gripping race against time. Can the process of planet formation, the clumping of dust into pebbles and then into planetary cores, happen fast enough inside these beleaguered disks before the gas reservoir is completely boiled away? The answer may define what kinds of planetary systems emerge from such violent nurseries. In a disk that loses its gas quickly, you might only get rocky, terrestrial planets like Earth or Mars, as those worlds form from the dust that remains after the gas is gone. The formation of gas giants like Jupiter or Saturn, however, requires a massive atmosphere of hydrogen and helium to be available for a growing core to capture. If the gas evaporates too swiftly, that opportunity vanishes. So the proplyds we see with long, streaming tails might be giving birth to only rocky worlds, or perhaps to no planets at all if the evaporation is too efficient. Their fate is a stark reminder that location is everything in the universe. Being born near brilliant, massive stars grants a spectacular view but may come at the ultimate cost, the loss of a future filled with diverse worlds. This desperate race against evaporation is just one small drama within a structure of staggering scale. Our view of the Orion Nebula is a trick of perspective, a celestial alignment of breathtaking luck. To the naked eye, it appears as the fuzzy middle star in the sword hanging from the belt of the great hunter Orion. But this is no star. It is a window, a brilliantly lit porthole we happen to be looking directly through into a hidden realm. The glowing cloud we so admire is merely the illuminated tip of a cosmic iceberg. It is the closest and brightest part of an immense, dark structure known as the Orion Molecular Cloud Complex. This complex is a sprawling network of cold gas and dust hundreds of light years across, a vast stellar factory hidden in plain sight. Within this colossal complex, the visible Orion Nebula is just one active construction zone, a blister on the surface of a much larger, mostly invisible body. Other famous sites, like the Horsehead Nebula and the Flame Nebula nearby, are also part of this same gigantic complex, different facets of the same monumental cloud. Our fortunate line of sight view from Earth places the Trapezium cluster right at the front, blazing like a lighthouse. Its intense radiation excites the gas directly in front of it, creating the glowing cavity we see, while behind it stretches leagues of unlit, dense material where future stars are already coalescing in the dark. So when you look at that fuzzy spot in the sword, you are not looking at an isolated object. You are peering down the barrel of a cosmic assembly line, seeing the one spot where the lights are on, while all around it, in every direction, the unseen work of building stars and planets continues on a scale that dwarfs our imagination. This alignment reminds us that the universe is a place of profound depth, where a single point of light can be the gateway to an entire hidden world. Hidden within the nebula's radio whispers is a signal that defies simple explanation. For decades, astronomers mapping the sky in microwave wavelengths noticed a faint, diffuse glow coming from clouds like Orion, a glow that simply didn't fit. It couldn't be explained by the thermal radiation from warm dust, nor by the synchrotron radiation from electrons spiraling in magnetic fields. This mysterious energy was dubbed anomalous microwave emission, and it became a quiet puzzle in the background of cosmic studies. The key to unraveling it lay not in vast structures, but in the almost unimaginably small. The leading hypothesis points to nanoparticles, specks of matter so tiny they contain only a few hundred to a few thousand atoms. Think of them as interstellar soot, or, even more intriguingly, as minuscule diamonds, forged in the atmospheres of cool, aging stars and then blown into space. These carbon nanoparticles are theorized to carry a slight electric charge. As they tumble and spin at incredible speeds, driven by collisions with atoms or even by the energy of starlight itself, their rotating charge generates radiation. It is a process called electric dipole emission, and it broadcasts in the microwave band, producing that subtle, anomalous glow that permeates the nebula. This discovery is profound because it suggests a previously overlooked component of the interstellar medium. We are used to thinking of space as filled with gas atoms, dust grains, and radiation. But the anomalous microwave emission hints at an entire hidden population of macromolecules, a fine mist of complex carbon compounds drifting between the stars. These nanoparticles are more than just curiosities. They could be vital pieces of the cosmic life cycle. They are likely the seeds from which larger dust grains grow, and they may also be carriers of complex organic molecules. Their presence in Orion, a place of both destruction and creation, implies they are resilient, able to survive the harsh environment of a stellar nursery, and perhaps even be incorporated into new planetary systems. So this faint microwave whisper is a reminder that the cosmos is filled with components we are only just learning to detect, where even the tiniest spinning specks can illuminate the grandest clouds. The nebula's hidden history is written in the ages of its stars. If you could line up every star in the Orion Nebula and ask them their birthday, you would not get a single uniform answer. We often picture stellar nurseries as places where a whole generation of stars is born together, like a single brood of chicks hatching at once. Orion tells a more complex story. The brilliant, massive stars of the central Trapezium cluster are cosmic newborns, just about 1 million years old. In stellar terms, they are infants who have barely opened their eyes. Yet, scattered throughout the wider region are stars that are slightly older, perhaps 2 or 3 million years of age. That difference might sound trivial, but on the rapid timeline of massive star formation, it is significant. It means these stars are not siblings from the same litter, but more like cousins from successive litters. This age spread is a crucial clue, revealing that star formation in this cloud has not been a single explosive event. Instead, it has been an ongoing process, likely occurring in distinct bursts or waves over several million years. Think of it like a city being built not all at once, but neighborhood by neighborhood. The first wave of star formation, those slightly older stars, may have begun in a denser part of the original molecular cloud. The radiation and winds from those first stars then compressed nearby gas, triggering the next wave of collapses, which ultimately produced the Trapezium cluster we see today. This sequential, self-propagating star formation helps explain the nebula's complex structure and dynamic activity. It is not a static snapshot of creation, but a multi-generational saga, where the oldest stars are still shining while the youngest are taking their first breaths, all within the same glowing cloud. This ongoing cycle suggests the nursery has been active for longer than we might guess, and that its final, dazzling display is the culmination of millions of years of quiet preparation in the dark. These multi-generational stars are all born from darkness, and sometimes we can see that primal material in its most elegant form. Among the nebula's most breathtaking sights are the silhouette disks, dark and sharply defined against the luminous gas. The Hubble Space Telescope has captured several of these perfect cosmic cameos. They appear as crisp black circles or ovals floating like holes in the fabric of light. The most famous example is often called the dark disk or silhouette disk 1, a nearly perfect black spot with a faint, glowing rim. What we are seeing is not a hole but a solid object. These are protoplanetary disks, the same propellets that can glow when seen face-on, but here we are viewing them from the side, edge-on. Our line of sight skims right along the plane of the disk, so the thick central band of dust and gas completely blocks the brilliant light of the nebula shining behind it. It is a celestial eclipse caused not by a planet but by an infant solar system. This perspective is a gift to astronomers. While a face-on glowing disk reveals its hot, inner regions and jets, an edge-on silhouette provides a direct measurement of something much harder to see, the disk's true physical structure. The sharpness of the shadow tells us about the density and distribution of the dust. The size of the dark patch reveals the disk's diameter, often hundreds of times wider than the orbit of Pluto. Some silhouette disks even show a subtle, reddish glow around their edges, starlight from the central infant sun peeking over and under the dusty rim, highlighting the disk's thickness. By studying these silhouettes, scientists can take a census of the dust grains within, understanding their size and composition. This is the raw material for future planets, and seeing it in stark outline allows us to measure the very ingredients available for construction. Each one of these dark cutouts is a blueprint, a profile view of a potential solar system under assembly, framed by the violent beauty of the nebula that created it. But the forces that sculpt this nursery may reach back far deeper into the past to events of unimaginable violence. That subtle age difference among Orion's stars points to a hidden trigger. The current burst of activity that lit up the Trapezium and the glowing nebula likely did not begin spontaneously. It may have been set in motion by a stellar cataclysm that occurred long before any of these visible stars were born. The culprit is a supernova, the explosive death of a massive star from an earlier, forgotten generation within the vast Orion cloud. Picture a solitary giant star, born perhaps 10 million years ago from a different part of the same molecular complex. It lived its short, brilliant life and then ended it in a shattering detonation, unleashing more energy in seconds than our Sun will in its entire lifetime. The expanding shell of debris from that blast, moving at a fraction of the speed of light, would have raced outward for centuries, a colossal shockwave plowing through the surrounding dark clouds. When such a shockwave slams into a quiet, dense pocket of interstellar gas, it does not simply pass through. It acts like a cosmic snowplow, compressing the material ahead of it into an incredibly dense, turbulent sheet. This violent squeeze can overwhelm the cloud's internal support, pushing pockets of gas over the critical threshold where gravity takes control. In essence, a supernova shockwave can kickstart star formation on a grand scale, turning a placid cloud into a bustling stellar nursery. This process, called supernova-induced star formation, is a compelling theory for what ignited the most recent and spectacular wave of births in Orion. The shockwave from that ancient explosion would have swept through the cloud millions of years ago, setting the stage. The first stars to form from that compressed material are the slightly older ones we see scattered around the region. Then, their own winds and radiation further agitated the cloud, leading to the collapse that created the infant Trapezium cluster. So the glorious nebula we admire today, a symbol of cosmic birth, might very well be the legacy of a monumental death. The brilliant glow of new stars is, in a very real sense, illuminated by the echoes of an old one's final act. This cycle turns the universe into a perpetual engine, where the end of one stellar story provides the opening chapter for countless new ones. The spinning carbon dust and ancient supernova echoes are not the only hidden signals broadcasting from the nursery. If you could tune a radio telescope to a very specific frequency, you would hear another kind of cosmic laser, one that crackles with the energy of water in motion. These are water masers, and they are born in the most violent neighborhoods around newborn stars. While methanol masers form in shocked regions, water masers require an even more extreme environment. They flare to life within the high-speed outflows and jets that erupt from the poles of protostars, where temperatures soar to 1,000 degrees and shockwaves rip through the surrounding gas. In this maelstrom, water molecules, likely freed from icy dust grains by the intense heat, become supercharged. They are excited by the relentless collisions, and just like with methanol, they begin to amplify passing microwave photons, creating intensely bright, pinpoint beacons of radio emission. These masers are more than just natural amplifiers, they are brilliant tracers of chaos. Because they only switch on under such specific, extreme conditions, each glowing spot of water maser emission acts like a flare gun marking a site of violent interaction. When astronomers map them, they often find the masers lined up in a row, tracing the path of a protostellar jet as it plows into the surrounding cloud. Others appear in tight clusters, highlighting the turbulent working surface where a jet slams to a sudden halt. By measuring the precise Doppler shift of the microwave light from each maser spot, scientists can calculate its velocity, revealing whether that pocket of water is rushing toward us or flying away at hundreds of kilometers per second. This allows them to construct a three-dimensional map of the outflow's structure and power, seeing not just a blurry image but a dynamic model of the forces at play. The geometry they reveal is astonishing. Some outflows are tightly focused like a fire hose, while others are wide-angled, more like an opening fan. Water masers help distinguish these patterns, showing us how the star is interacting with its birthplace. The energy involved is staggering. These jets can carry away a significant fraction of the star's gravitational energy, acting as a crucial release valve that allows the infant sun to finally settle into a stable state. So every flickering point of water maser emission is a direct measurement of a star's birth cry, a signal from the very mechanism that allows a chaotic ball of gas to become a stable, shining sun. It is a reminder that the violence of creation is not random, but a finely tuned, fundamental process, and we can listen to its signature in the faint whisper of excited water. The faint whispers of water masers map a violence that can sculpt the nebula on its grandest scale. Peering through the obscuring dust with infrared eyes, space telescopes like Spitzer have unveiled a hidden skeleton within Orion. Stretching far from the nebula's chaotic core is a vast, faint structure shaped like a cosmic letter X. This is not a collection of stars, but an immense formation of warm dust and gas, an architectural blueprint written in heat. Its symmetrical arms extend for light years, a ghostly imprint that visible light could never reveal. The discovery of this X-shape immediately posed a profound question: what kind of force leaves a signature that large and that organized? One compelling theory points back to the fury of the nebula's most massive stars. Their powerful bipolar outflows, jets erupting from their poles in opposite directions, could have carved out two gigantic, cone-shaped cavities within the surrounding molecular cloud over hundreds of thousands of years. Our infrared view from Earth, looking down the axis of these cavities, would see their glowing walls projected onto the sky, forming the distinct arms of an X. It is the fossilized outline of stellar breath on a galactic scale. Another, more explosive idea suggests this shape is the remnant shrapnel of a colossal detonation. A close encounter or merger between massive protostars or even a supernova from a vanished predecessor star could have blasted material outward in a symmetrical cross-like pattern. The expanding shockwave would have shaped the surrounding dust into this enduring form, a permanent scar from a single ancient cataclysm. Yet a third possibility weaves in an even more fundamental force. The shape could be the direct imprint of the molecular cloud's original magnetic field. As the cloud first collapsed, its magnetic field lines would have guided and confined the infalling material, much like iron filings aligning to a magnet. This could have funneled gas and dust into a preferred orientation, creating an inherent cross-shaped structure in the cloud's density long before the trapezium stars ever ignited. The infrared X, therefore, is more than a curious shape. It is a forensic clue, a choice between three grand narratives. Was it sculpted by the steady winds of living stars, the sudden blast of a stellar death, or the patient hand of magnetism during the cloud's very birth? Each answer tells a different story about the forces that built this iconic nursery. The vast, symmetrical X hints at a history of powerful ejections, and sometimes the objects flung away are not stars at all. Drifting in the lonely spaces between the stars of the Orion Nebula are some of its most perplexing residents, the free-floating planetary mass objects. These are cosmic nomads, bodies with masses similar to Jupiter or Saturn, yet they travel entirely alone, unattached to any sun. Their discovery immediately sparked a fundamental question: what exactly are we looking at? The first possibility is that they are the smallest of the failed stars, objects known as brown dwarfs. A brown dwarf forms just like a star from the direct collapse of a gas cloud, but it simply never accumulates enough mass to ignite sustained hydrogen fusion in its core. It is a stellar underachiever, glowing faintly with the leftover heat of its birth before slowly cooling into darkness. The free floaters in Orion could represent the extreme low-mass tail of this population, objects so small they blur the line between a failed star and a superplanet. The other, more dramatic possibility is that these are true planets but orphans. In the violent gravitational pinball of the young Trapezium cluster, a close encounter between stars could have ripped a giant planet from its orbit and sent it careening into interstellar space. A newborn gas giant, barely formed in its disk, could be flung away on a permanent exile, destined to wander the cold void alone. This idea forces us to reconsider what a planet is. Our classic definition requires it to orbit a star, but if a body of planetary mass and composition is formed in a disk and then ejected, does it stop being a planet? Or if a cloud collapses directly into a Jupiter mass ball, is that a planet or a star? Orion's free floaters present this classification crisis in real time. Their very existence challenges our neat categories and suggests the universe operates on a continuum. Whether they are ejected planets or diminutive brown dwarfs, their presence tells us that the nebula's turbulent dynamics can produce isolated worlds, and that planet mass objects may be far more common in the galaxy than we ever guessed, many of them perhaps living solitary lives in the eternal night between the stars. These wandering worlds and vast infrared shapes all dance to the tune of an invisible conductor. The Orion Nebula is threaded with powerful magnetic fields, lines of force that weave through the gas and dust like the hidden threads of a cosmic tapestry. While we cannot see magnetism directly, its influence is everywhere, sculpting the grand architecture and guiding the smallest motions. Astronomers map these fields using a clever trick of light. As starlight passes through clouds of elongated dust grains, those grains align themselves with the local magnetic field like countless tiny compass needles. This alignment polarizes the light, causing it to vibrate in a preferred direction. By measuring this polarization across the nebula, scientists can trace the field's orientation, revealing its otherwise invisible line. The maps they produce are fascinating and puzzling. In the long, quiet filaments like the integral-shaped feature, the magnetic field lines are remarkably ordered, running neatly along the length of the structure like wires in a cable. Here, magnetism appears to be a stabilizing force, providing a rigid skeleton that supports the cloud against its own gravity, potentially slowing down star formation. But near the violent outflows from newborn stars, the picture shatters into chaos. The fierce jets and stellar winds act like cosmic wrecking balls, tangling and twisting the magnetic lines into knots. In these regions, the field is no longer a calm guide. It is a participant in the turmoil, being stretched, compressed, and dragged along with the supersonic flows. This stark contrast lies at the heart of a major debate in astrophysics. What is the true role of magnetism in a stellar nursery? Is it primarily a supporting structure, holding clouds up and regulating the pace of star birth? Or is it an active guide, channeling material along its lines into dense cores where gravity can finally take over? The evidence in Orion suggests it might be both, a dual nature force that initially resists collapse but once gravity gains the upper hand, helps orchestrate the final act of star formation. This magnetic mystery reminds us that the universe is built on forces we are only beginning to map, where the invisible framework may ultimately decide the fate of everything we see. The invisible magnetic fields that shape this nursery will ultimately witness its final transformation. Every stellar nursery has a lifespan, and the Orion Nebula's clock is already ticking. The very stars that illuminate its beauty are the agents of its inevitable destruction. The brilliant, massive stars of the Trapezium cluster live lives of furious intensity, burning through their nuclear fuel in just a few million years, a mere blink compared to our Sun's 10 billion-year lifespan. Their destiny is not a quiet fade, but a cataclysmic finale. One by one, these titans will exhaust the hydrogen in their cores, collapse under their own weight, and then rebound in titanic supernova explosions. Each detonation will unleash more energy than our Sun will produce in its entire existence. Imagine the shockwave from a single such blast, a sphere of pure energy expanding at a significant fraction of the speed of light, slamming into the delicate structures of the nebula. The remaining tendrils of glowing gas, the dark lanes like the fish's mouth, and any lingering protoplanetary disks will be violently shredded, heated, and swept away. The iconic cloud we know will be utterly dissolved, its material blasted into the surrounding interstellar medium. This is not merely an end, however, it is a necessary rebirth. In their deaths, these massive stars perform their most vital cosmic duty. The furnaces of their cores and the violence of their explosions forge the heaviest elements, atoms like iron, silicon, oxygen, and carbon. The supernova blasts will seed the expanding cloud of debris with this enriched material, a chemical legacy carried forward. That enriched gas, now laced with the elements for rock, water, and life, will eventually mix with other interstellar clouds. Millions of years later, as this enriched material collapses under gravity to form a new generation of stars and planets, those new worlds will be built from stardust forged in Orion's final fire. They will have a richer, more complex chemistry from their very beginning. So the dispersal of the Orion Nebula is a poignant closing chapter for one celestial landmark, but it is the opening sentence for countless stories yet to be written across the galaxy. The nebula's ultimate fate reminds us that in the cosmos, destruction and creation are two sides of the same coin, and an ending here is always a beginning somewhere else. This journey through 25 strange phenomena reveals a single, stunning truth. The Orion Nebula is not a static painting in the sky, but a living, breathing, and often violent cosmic laboratory. Its beauty is the side effect of physics operating at an extreme scale, a luminous byproduct of creation itself. We have wandered from the photodissociation frontier of the Orion Bar to the hidden infrared furnaces of the Kleinman Low Nebula. We have witnessed infant solar systems forming in silhouette disks and evaporating under stellar blowtorches. we have traced the paths of runaway stars, cosmic bullets, and the faint microwave whispers of spinning nanoparticles. Each phenomenon, from the vast magnetic X to the delicate chemistry brewing on dust grains, is a piece of a grand puzzle. Together, they show us that the birth of stars and planets is a messy, chaotic, and breathtakingly beautiful process, one that builds the very elements of life amidst the turmoil. The next time you find yourself under a dark sky, look for the 3 stars of Orion's belt. Just below them, find that fuzzy patch in his sword. Remember, you are not just looking at a distant cloud. You are gazing into a window of our own cosmic origin story, a place where the universe is actively building its future. Which of these 25 phenomena left you the most awestruck? Let us know in the comments below, and if you enjoyed this deep dive into space's mysteries, be sure to subscribe. There are always more wonders waiting just beyond the light.